Good afternoon, boys and girls. We are back talking about applications of capacitors. But before that, I want to make a reminder to you that when capacitors have been arranged in series, we say that 1 over C total is going to be 1 over C1 plus 1 over C2 plus 1 over C3, depending on how many resistors we are having. This one is in series. But when you talk about capacitors in parallel, we are saying that this one, we say C total is going to be C1 plus C2 plus C3. And I remember explaining this very well when we are doing some experiment, when we are doing some examples over the same. What you need to note is that under in series, we are saying that there is a sharing of current all through. But when you come to this one, the quantity of charge is actually the same all through. We have to be very careful, especially when you are doing some examples of equations or questions in a particular setup. Now, applications of capacitors, there are so many. We are something we call rectification. We'll be talking about in details when we talk about electronics in Form 4, but under this we say rectification is actually done by what you call capacitors when you are doing what you call smoothing of circuits. And of course, we know very well that for any complete circuit to be complete, we have to have a capacitor or we have to have a diode in that particular circuit so that we can rectify or we can smooth what you call the circuit. Now, in these conversions, in the conversions of AC or what you call the continuing current, alternating current to DC, we use what you call diodes and a capacitor that we can use to maintain the high direct current voltage, and this is called smoothing or what you call a rectification. Now, I want to emphasize here, these are conversions. Most of these electronic gadgets we're having, they actually use what you call the direct current. But you see, there is a conversion that takes place when you connect any gadget to a current, what you call the circuit, the normal circuit you're using at home. What we use is what you call the alternating current. But what happens is, some of it and most of the alternating current has to be converted to direct current. That's why we use what you call the diode, and of course we need what you call a capacitor in that case. Now, of course, the process, by that process is what you call the smoothing or what you call rectification. So we are saying that one we need a capacitor, and that one is the application of what you are talking about. Reduction of sparking in induction coil, of course this will be talking about the heating effect, and of course we have what you call the coil, and this one is in the induction coil, whereby we need the reducing of sparking in the induction coil. A capacitor is included in the primary circuit of this induction coil to actually reduce the sparking. Sparking is that effect. You can see that the effect of that splashing of kind of those shocks we can actually reduce it by actually introducing a capacitor in the primary circuit. At the same time, in the tuning circuits, of course, when you talk about tuning, maybe we have an FM frequency, what you call the frequency modulation. The radio or the TV, we have what you call a variable capacitor that we are able connected in parallel, that now we are going to tune it so that now we can be able to do it, to make sure that we have a fine frequency modulation. Maybe you're listening to a radio, you want a clear message from the radio station, maybe it's Capital FM or even Citizen. So we're actually using a variable capacitor so that now we can be connected to parallel to inductor in the tuning circuit so that we can have what you call the radio receiver. That one can only happen in what we call a tuning circuit, and that one is an application of what we are talking about, a capacitor. Now, when the capacitance of a variable capacitor is varied, the electrical oscillations between the capacitor and the inductor changes. We are saying that we are varying what we call the capacitance, and of course you know how we can find capacitance. Right? If you are given a circuit, if you have been given several capacitors, we can actually get the total capacitance in this circuit. So by you varying that particular capacitance, by having the what you call the variable resistor, the electrical oscillations between the capacitor and the inductor will actually change. Either it will actually increase or it will reduce depending on how you are going to vary. Now, if the frequency of the oscillations is equal to the frequency of the radio signal, at the aerial of the radio, what will happen is the signal is actually received That's why when you are tuning the radio, there is a knob, the rotational knob, so that now you are able to reduce you are able to reduce by actually changing the oscillation. When you are doing that now, you are actually affecting the receiver, the signal of the receiving radio. So that by doing so, you are actually regulating the frequency of the radio signal, and thereafter what happens is you are able to have the change in this one here. Now also we have what you call the delay circuit. Capacitors are actually using the delay circuit designed to give intermittent flow of current and in a car indicators. That's why, for example, if you are having a delay circuit, so that now there is actually that flow of the electric current, and that can only be done by what you call the delay circuit, and that one is a part of an application of this one here. In a camera flash, we have a capacitor in the flash circuit of a camera that is actually charged by the cell in the circuit. When in use, the capacitor discharges instantly to flash, and that one is actually being done by the capacitor. Remember, when you're talking about the charging and discharging of a capacitor, when a capacitor is full, is able now to release the energy or the charge in form of energy. That way able to instantly release a flash, and that one can only be done in a camera. But clear observation is going to be made in the video. Just listen to it carefully. It's going to explain everything that entails the applications, and from there we'll also watch another video.
Hello, Dan Gopski here from howtomechatronics.com. In this tutorial we will learn what capacitor is, how it works, and take a look at some basic application examples. There is almost no circuit which doesn't have a capacitor on it, and along with resistors and inductors, they are the basic passive components that we use in electronics. A capacitor is a device capable of storing energy in a form of electric charge. Compared to a same-size battery, a capacitor can store much smaller amount of energy, around 10,000 times smaller, but useful enough for so many circuit designs. A capacitor is constructed out of two metal plates, separated by an insulating material called dielectric. The plates are conductive, and they are usually made of aluminum or other metals, while the dielectric can be made of any kind of insulating material, such as paper, glass, ceramic, or anything that obstructs the flow of the current. The capacitance of a capacitor, measured in farads, is directly proportional to the surface area of the two plates, as well as the permittivity of the dielectric, while the smaller the distance between the plates, the greater the capacitance. That being said, now let's take a look how a capacitor works. First, we can note that a metal typically has an equal amount of positively and negatively charged particles, which means it's electrically neutral. If we connect a power source or a battery to the metal plates of the capacitors, a current will try to flow, or the electrons from the plate connected to the positive lead of the battery will start moving to the plate connected to the negative lead of the battery. However, because of the dielectric between the plates, the electrons won't be able to pass through the capacitor, so they will start accumulating on the plate. After a certain number of electrons accumulated on the plate, the battery will have insufficient energy to push any new electrons to enter the plate because of the repulsion of those electrons which are already there. At this point, the capacitor is actually fully charged. The first plate has developed a net negative charge, and the second plate has developed an equal net positive charge, creating an electric field with an attractive force between them, which holds the charge of the capacitor. Let's take a look how the dielectric can increase the capacitance of a capacitor. A dielectric contains molecules that are polar, which means that they can change their orientation based on the charges of the two plates. So, the molecules align themselves with the electric field in such a way enabling more electrons to be attracted to the negative plate, while repelling more electrons out of the positive plate. So, once the capacitor is fully charged, If we remove the battery, it will hold the electric charge for a long time, acting as energy storage. Now, if we shorten the two ends of the capacitor through a load, the current will start flowing through the load. The accumulated electrons from the first plate will start moving to the second plate until both plates become back again electrically neutral. So that's the basic working principle of a capacitor, and now let's take a look at some application examples. Decoupling capacitors or bypass capacitors are a typical example. Decoupling capacitors are often used along with integrated circuits, and they are placed between the power source and the ground of the IC. Their job is to filter any noise in the power supply, like voltage ripples, which occur when the power supply for a very short period of time drops its voltage, or when a portion of a circuit is switched, causing fluctuations in the power supply. At that moment, when the voltage drop occurs, the capacitor will temporarily act as a power supply, bypassing the main power supply. Another typical examples are capacitors used in DC adapters. For converting the AC voltage into a DC voltage, a diode rectifier is usually used, but without the help of capacitors, it won't be able to do the job. The output of a rectifier is a waveform. So, while the output of the rectifier rises, the capacitor charges, and while the output of the rectifier declines, the capacitor discharges, and in that way smooth the DC output. Signal filtering is another application example of capacitors. Because of their specific response time, they are able to block low frequency signals, while allowing higher frequency to pass through. This is used in radio receivers for tuning out undesired frequencies, and in crossover circuits inside speakers for separating the low frequencies for the subwoofer and the higher frequencies for the tweeter. Another rather obvious use of capacitors is for energy storage and supply. Although they can store considerably lower energy compared to the same size battery, their lifespan is much better and they are capable of delivering energy much faster, which makes them more suitable for applications where high bursts of power is needed. So that would be all for this tutorial, but you can always find more details and tutorials on my website, howtomechatronics.com. Thanks for watching.
Now it's very clear when you look at this that the applications of a capacitor, they are varied depending on the size of the object, maybe the electronic gadget you are using, but of course the clear observations, the clear explanation has been made on this particular video. Now we are going to another video that is going to explain further the applications of the capacitors in detail, looking at the introduction, looking at the capacitor, the types of capacitors, and how we can even charge and so forth, and up to the explanation and to the same. Now, just before that, we go to the next. Before that, we are going to look at the next video, please.